Okay, so I don't have a polarizing filter or a polarizing lens here, at least not the kind that we use in the lab. What I do have are these polarized sunglasses. Now the polarization of the lenses on these sunglasses, and I have confirmed that these are polarized, not getting ripped off here. The polarization of these lenses works exactly the same as the polarization of the filters we use in the lab. The only difference here is that these are tinted and they've got this reflective coating on them, which means that when you look through them, you'll see some redness, and I'm going to show you a couple things through these. But just keep in mind that the redness is just the tint of the sunglasses, and the polarization of this lens works exactly the same. Now, it's a little hard to hold these in front of the camera and rotate them, but I'm going to show you a demonstration of a couple different things through here. Remember, if you look at unpolarized light or natural light, what you'll see as you rotate a polarizing lens, I'm going to use my sunglasses, what you'll notice is that the light doesn't really change intensity. That's because there's every different polarization already existing in that light, and so when I rotate it, I'm basically going to see the same amount of light come through at any angle. But the difference between looking at a polarized source is when you rotate it, you'll see you'll see a spot that's bright, or I shouldn't say a spot. As you rotate it, one angle, when the angle of the direction of polarization of these lenses lines up with the polarization of that light source, you'll see brightly through them, you'll see all the light come through. But when you rotate them 90 degrees to that, and the direction of polarization of the sunglasses is perpendicular to the direction of polarization of the light, you'll see basically nothing. You'll see pitch black through here. And from having done this demonstration already through the camera, it won't be pitch black because you'll see the reflection of the camera in the lens. That's just because the other side is now darker and you get a reflection instead, but it should be pretty clear. All right, the first one is these normal light bulbs in my ceiling fan here. I'm gonna go ahead and hold these sunglasses in front of the lens, and we will go ahead and rotate them. And it might go in and out of focus a little bit, but we'll see sort of what we expected, right? There's basically no change in the brightness of the lights that we're seeing, which tells us that this light coming from these light bulbs is unpolarized. It's natural light. And that fits with what people have discovered about light bulbs. So these are unpolarized lights. Now, it's kind of tough to have an unpolarized example first because you don't really know what polarization looks like yet, but the next one will be a polarized example. All right, the second example here is a computer screen. So here I have a little image for Earth Day pulled up. I know it's yesterday, but still good to celebrate the Earth. So here is what this looks like through the lens. Now remember, this is on my computer screen here. So notice how the brightness of that image really changes as I rotate these sunglasses down. It blocks almost all of the light out here. And remember, this is how my sunglasses are oriented here. Yeah, that's a good example. You can see the lens, see bright through it, and it gets super dark. And you can actually see almost nothing through there. So this is a really good example of polarization. So the light coming off of this computer screen is polarized. The last example I'm going to show you is light that's been reflected off of a surface, specifically unpolarized light that's been reflected off of a surface. So I didn't mention it before, but sunlight outside coming from outside is unpolarized. And so right here on this glass surface, you can see the reflection of some trees and stuff from outside, and so that light coming into this glass surface is considered unpolarized. Now let's see what the reflection of that unpolarized light looks like through the sunglasses. So we're getting a little bit of reflection off of the camera lens here, but look how bright you can see the trees in that picture. And as I rotate it, they disappear. Let me hold it out here a little bit further and maybe that'll help. It's tough to see most of them. And then as you rotate it, you can see most of the light and it goes dark. Okay, so that tells us that the light that's being reflected off of this surface is actually polarized, or at least partially polarized, because if you notice, you can still see just a little bit of light right here coming through that's natural light, or that was natural light. Let's talk about that last one for a sec. We know light can be polarized when it passes through a polarizing lens. There's actually one other way it can be polarized. If it reflects off of some reflective surface, let's say glass, because that's what we saw in the last example. It could be water, it could be other stuff, but we'll take glass for now. Now, if the light coming in is unpolarized, remember that means that we've got polarization directions all over the place. But the light that reflects off the surface is actually partially polarized. And the percentage of light in the reflected ray that is polarized depends on the angle that you come in at, the index of refraction of glass, and the index of refraction of air. Now, there's one perfect angle called Brewster's angle, and it depends on the material. But when your light comes in at Brewster's angle, 100% of the light that's reflected is polarized. Now, if you're not at Brewster's angle, some of the light here is still polarized, but not all of it. We can actually still make use of this. So, the best example I can think of this is actually with the sunglasses. The sunglass companies polarizing their lenses. So, polarized lenses are really nice when you're in a place that has a lot of reflection, like maybe in the snow. The snow has a ton of reflection of sunlight that gets in your eyes and can kind of hurt them over time. And same with water. Water reflects stuff really well. So if you're at the beach or if you're on a mountain maybe, polarized sunglasses can actually really help out. The reason being is if the company has polarized them correctly, which we know a lot of companies actually cheat and maybe don't polarize, they just tell you they're polarized, or they polarize them poorly. But these are a pretty good polarized pair. So if they've lined up the polarizations correctly in the lenses, they can actually block out the percentage of light that comes in the reflection that is polarized. So let me say that one more time. If your polarization in your sunglasses is set up correctly, any portion of reflected light that's polarized will be blocked from your eyes. And that's how we cut down the intensity that actually gets into our eye by wearing polarized sunglasses. Now, sunglasses can cut down other ways. There's obviously unpolarized sunglasses, which are just darker lenses, material that's harder for the light to get through. But with the polarization, you can specifically cut down on the amount of light that comes from reflections, which is super nice. Now, if you ever go out to buy a pair of sunglasses and you think that they might be ripping you off about whether or not they're polarized, there's an easy way to check. Now, I can't demonstrate it here because I only have one pair. Well, there's two easy ways to check. Grab another pair and hold them at 90 degrees to each other. So if this is my other pair, I'm going to put a lens up to and see if it blocks out the light. And if it doesn't, you can rotate them. And remember, if you ever see the light get completely blocked out, you know that they're polarized. But if the light always looks like the same intensity as you're rotating them through, those lenses aren't polarized. The last way, if you really don't have that, is you could look at a digital screen like we saw with the computer screen. You can point the lenses at the computer screen, rotate them, and if you see the light intensity go down or back up, you know that they're polarized. And of course, if it looks the same, you're getting ripped off.